All right, today we're going to discuss the different number systems throughout history, because the system we use now actually is on the very bottom of this list. It's Hindu Arabic, because that's the word algebra is an Arabic word, al-jibr. It's from the region of algebra, of Jabbar. So this is how it went through for thousands of years. Because again, they needed it for commerce. How many sheep and how many goats am I trading? So this is where it all came about. And it all started with tally marks. Just making notches of how many you have. Well, again, that wasn't too structured, because what if you had 100 or 200 or 300? Then you have to count each one of these hash marks, which is why we have these other systems. All right, the first one we get to see what I want to talk about are the Egyptians. The Egyptian system actually, this is the corresponding values of our base 10 system. 1, 2, 3, 4. There's 5 hash marks and so on and so forth. But once you get to 10, that's when we get the heel bone. And this is the numeric system for the Egyptian system. Instead of a hash mark, because remember, Egyptians used hieroglyphics, which are pictures to represent words and numbers. So you guys don't have this. That's it. I'll upload these sheets on Blackboard later on. But yeah, these, and I should have made a copy of just these systems instead of that first one I gave you. So, but this is what we're going to deal with. So go ahead and write these down. The hash marks, the vertical staffs, were the face values of 1 each. The heel bone represented 10. The scroll looks like a 9, represents 100. The lotus flower was 1,000. The pointing finger was 10,000. The Pawag, or whatever that is, and their times was 100,000. And the astonished man was 1 million. So what if we had, it says down here, what number would that be? So what is this first symbol? Yeah, it's a Pawag, so that's 100,000. And each of these represent what? So you have 3 of them. That's 300. And these, that represents 10 each, so that's 20. And then there's 2 of those. Combining all those, we get 100,322. You remember, the Egyptians were very, very, very graphic people. That's all they dealt with, was pictures that had symbolic meaning. Looking at our system, what does this number represent? The ones and this, and then so on and so forth. That became the next big invention, the placeholders. If I have a number here, what does that mean? That means I have whatever number this is. For example, if I had, that means I had 3 1000s, 2 100s, 1 10, and 1 1. So you finished? That was brought about by the Babylonians. They only had these two symbols for theirs, the ones and the tens. You guys don't have that either. These, I'm lecturing up here. You don't have any of those. Well, we're going to reference back to those. That's why I want you to copy these on your notes, because the second sheet I gave you is a worksheet that goes through these examples. Yeah, so the upside down triangle represents the ones, and the less than symbol represents 10. But in the Babylonian system, they had place values. So in this first place value were the numbers 1 through 59. The next one was the 60s place value. The next one was 60 times 60 place value. And what do you think the next one's going to be? 60 times 60 times 60, right? And the reason they used a arbitrary number like 59, one theory summarizes that the number of fingers in a hand, you have 5, and once you get to this one, where do I go after this? So that's one theory. A lot of their, remember, the way they kept their information was on stone, and a lot of the jungle still covers up a lot of things that we're still discovering. So let's look at these examples. Let's say I had what would that number be? Okay, there's 2 10s, which is how many? And that's a 1, right? But this is in the second placeholder value. So it's multiplied by 60. So 2 times 6 is 12 with 2 zeros, plus 1 equals 1201. Okay, what if I gave you this number? What number does that represent? What number is this? Look at your notes. You should have written down the system. Yep, very good. It's 11. It's a 10 plus a 1. So it's 11, but it's times what number? 60 times 60, because this is in the third location. And then this one, grab one of those packets over there. Then this one here is 11 times 60. And then this is in the ones column, so it's just a 1. So 60 times 60, 6 times 6 is 36 with 2 zeros. 11 times 6 is 66 with 1 0. Eleven times 36 is what? 396 with 2 zeros behind it. So adding all these together, get 39600, 6600 and 1. So it's 1, 6, 12, 0, 4, 4, 0, 2, 6, 1. We already know what this number is here. That we just did that. So what do we have to add to it? The downward triangle is what? So 1. And how many 60s are multiplied? Yeah, so it's 60 times 60 times 60. All this stuff equals 4261. 6 times 6 is 36. 36 times 6 is 216 with 3 zeros. It's 216. This right here equals 216000. And then these numbers is 4261. So that the last numbers are going to be 261. 4 plus 1 is 5. 2. I ran out of paper, so that's why I did it quick like that. That's at the bottom of the sheet. So that's the Babylonian. You see an obvious flaw with that? With that, this times 60. But again, the Babylonians were pretty advanced for their time too. What was Babylon? Remember, the first system we talked about was the Egyptian. Then we did the Babylonians. Are they in the same part of the world? Well, the Tower of Babylon, the Tower of Babel, that is near where Iran and Iraq is. And Egypt is not too far from there. It's just further down across the Red Sea in that part of Africa. So it's that half of the world. But the next one we're getting to now, the next system we're getting to is the Mayan number system. And as we'll see, the Mayans had a vertical numerical system. What do I mean by that? Is the nutshell is a 0, a single dot is a 1, and the line is a 5. So what would this number be? How about 17? 5, 10, 15, 16, 17. Because it's the same. We have 3 times 5s, 2 times 1. 15 plus 2 is 17. What would that number be? I'm not for sure. I'm trying to remember if this equaled 20. Don't quote me on that one. That's because the symbol itself just meant a 0. So, but again, don't quote me on that. Or maybe it was one of these two. That's this. The nutshell with a single dot represents 20. All right, so let's look at this number. If we had this numeric system, this number. Remember, it's a vertical numeric system. This is the 1s. These are the 20s. And the next one would be 20 times 20. So what number does this represent? What number is this? Yeah, 5, 10, 11, 12, 13. So it's 13 times 20, which is 260. And this number is 5, 10, 11 times 1, which is 11. Add those together, you get 271. So again, it's a vertical numeric system. So it's the ones, the 20s, the 20 times 18. It's not 20 times 20. As I remember, I was looking at my notes. The Mayans, for some reason, instead of going like the Babylonians and the Egyptians, were it just increased by the same number. For some reason, they changed from 20 to 18. And then everything after that was 18 when you multiplied higher numbers. Again, nobody knows why, because those documents, those records are not found. So if I gave you this number, make this one. That's a mistake. If I gave you this number, what number would it represent? Remember, it's 3. I mean, it's 6. So it's 6 times 20 times 18. This is the next level. So it's a what? 12 times 20. And this last one, 9 times 1, which is 9. So 20 times 18 is 360. 360 times 6 is 2160. That's the top number. So it's 2160. The next number is 12 times 20 is 24 or 240. And 9 times 1 is 9. 0 plus 9. 6 plus 4 is 10. 2409 is represented by this number here. So in the Mayan numbers, this is times 1, times 20, times 20, times 18, and so on and so forth. Times 18, times 18, right? Okay. The next evolutionary, let me see something. Hello, is the Roman numeral system. You've seen these a lot. They're on dollar bills, they're on buildings, they're on movie trailers. Whenever you see those, on the Super Bowl. On Super Bowl, we had your question you just asked about the Mayan system. You asked about 20 times. Let me see. In the Mayan system. So it was, let's say we had 5 levels. So this one's times 1. This one's times 20. This one's times 20 times 18. And then you asked what next after that? Oh, no, I'm sorry. No. Again, this is what the anomaly was. Everything else would be, there's only, again, this is where the anomaly was, why they put on the second, third level at 18. Because there's no reason for that. But it always, then the 20 repeats itself. It's base 20 system. And also, I'm gonna put another one here. I'm gonna put another one binary. But yeah, we'll talk about that last. Okay, so the Roman numeral system is based on these letters that have a specific meaning. A single number 1, that counts as a 1. A V is a 5. X is a 10. L is 50. C is 100. D is 500. And M for milli is 1,000. Centi, deci, deci, and milli. So centis, 100, 500, 1,000. So this number here would be what? L is what? V is an II. So it's 50 plus 7. So the super roll is number 57. But here's the stipulation. In Roman numerals, you cannot have more than 3 of the same letter. I'll put letter because that represents numbers in a row. So this is what this means. I'll put over here. This is the number 1. This would be the number 2. This would be the number 3. Okay, let me skip a space. And that's the number 5. You will never see 4 hash marks in a row. But what you will see to represent the number 4 is IV. The Romans were the first to use subtraction in their counting system. If a smaller letter is in front of a larger letter, you subtract that value. So the V is a 5. Since the I is in front of it, it says 5 minus 1 is 4. Let's do a couple of these. So that's 1. That's 2, 3, 4, 5. How would the next number look? That's 5 plus 1 is 6. VII. 5 plus 2 is 7. VIII. That's 5, 6, 7, 8. Remember, I can't have more than 3. So what's the next number going to look like? What's 9 going to look like? Yeah, IX. Very good. So it's 1 from 10, which is 9. And the next one is X, which is 10. What would that number be? 49. Very good. How about that number? What does X represent? That's 10. L is 50. So the smaller numbers in front, I subtract. 50 minus 10 is 40. So if the smaller numbers in front, you subtract that value from the bigger number. So this is actually 50 minus 10. X M. That's going to be M is millions, 1,000. X is 10. So this is 990. So if the smaller numbers afterwards, you add it. Smaller number is after a larger number, then you add. If the smaller number is before a larger number, then you subtract. If the numbers are the same, just add. So here's what those mean. If the smaller is before a larger, so I have something like this. It's 10 before 50. So it's 50 minus 10 equals 40. If this, oops, no, it's if it's after I'm sure. So if it was LX, that would mean what? 50 plus 10 is 60. If I had XL, that would be 50 minus 10, which would be 40. So if the smaller numbers after, you just add them. If it's before, you subtract them. If it's the same, 10 plus 10 makes it 20. Okay, let's test your knowledge now. Using these numbers, let's write our year, current year. in Roman numerals. Because this is what you'll see on movies. If you ever watch the trailers or anything, and you'll see where the copyright is, you'll see all these letters. This is how you read them. So how would you write 2023 or 2023? How would you write 2000? M. There's nothing in the hundreds. What's 20? X. And what's 3? That's 2023. Goes 1000 plus 1000 is 2000. 10 plus 10 is 20. 1 plus 1 plus 1 is 3. Okay, how about 1990? So do we have a symbol for this number? A 1. How do we represent 900? XM? Because 900 is, how do we get 900? Using these numbers. CM, yeah, because we have 1000 minus 100, so it's CM. That means it's 1900. How do we do 90? XC, very good. Because it's 90 is 10 before 100. All right, so now do your birth year. So go ahead and do your birth year and we'll do them together. Okay, give me somebody's birth year. Ooh, that's a good one. A lot of letters there. Okay, how do we write this one? See what? Over here. Okay, so this is 1. That's for 1000. 100 from 1000 is 900. How we get 90? XC, that's for 90. So this is 1000. This is 900. 90. And how we do 7? Right. So it's MCM XC VII. Who's got another birth year? 1991. Ooh, that's a lot of letters. Actually, no, it's gonna be pretty short because it's gonna be this. All right, let's see this. The 1. So that's M. This is 1,000. The next number, 900. No, because 900 is how far from 1,000? Well, it's 900 is 1,000 minus 100. So it's CM. $90 is 100 minus 10. So it's X. What's 100? C. M is 1,000. IX, very good. So your answer is MCMXCIX. Oops, IX. See, it looks cool when you put it in Roman numerals. I think it does. Okay, next birthday?
1992.
92?
M. CM. XC.
Very good. Excellent. And last one. That's an easy one. M&M. yeah, that's pretty easy. Okay, so that's how you convert from our numeric system to Roman numerals. Okay, tell me what this number is. So it's 1,000. 1,000 minus 10. And 8. Okay, but here's the problem with this. Because 1990 could be made another way, couldn't it? I mean, 990. That could be CM, that's for the 900. 90 is XC. So that's 1,000 minus 100, which is 900. 100 minus 10, which is 90. Add these together, you get 990. So in essence, I gave you a mistake. You can't use that large of a difference in numbers. In other words, what I'm saying there is before the X, you can use one of these two. Before the C, you can use a 50 or a 10, a D, one of these two, M, one of these two. So we knew what this meant, but 1998 would look like that. Also, there's another thing. What's the highest number we have on our list? Now, how do we get numbers bigger than that? Romans used the multiplicative property to represent very large numbers. With this bar. That bar means multiply by 1,000. So this would be 5 times 1,000 equals 5,000. How about that number? Okay, so it's 90 times plus 7. So it's 97 times 1,000. 97,000. But it's only wherever that bar is over. Because what if I had this? What number would that be? Because XC is 90 and VII is 7. So it's 90 times 1,000 plus 7. So it's 90 with 1, 2, 3, 4 zeros. 90,007. So far, so good. All right. The next is the Hindu Arabic. There you go. That's the Hindu Arabic number system. It's what we use today. It's a base 10 system. What does base 10 system mean? Basically, a base system, it tells us how many numbers before you go to the next level of numbers. What does that mean? Here are the ones. 0, 1, 2, 3, 5, 6, 7, 8, 9. After 9 comes what? 10. So this is the tens. 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. After 19, the 20s. 20, 21, 22, 23, 24, 25, 26, 27, 28, 29. How many numbers are there from 0 to 9? 10, which is why we call it the base 10 system. It has 10 numbers before it goes on to the next level. Because these, so this is only 1-digit numbers. And then all of these are 2-digit numbers. Not 20s. These are all 10s. Then we jump up to 100. 101, 102, 103, and so on and so forth. So these are now 3 digits. So we have 1-digit, 2-digit. Now we have 3 digits. What's the largest 3-digit number we can get? Yeah, all the way up to 999. Once we finish 999, we jump up to 1000. We got 4 digits. So our number system is a base 10. For example, 9,762. How is that number made up? It's 9 times 1,000. That's this number. 7 times what number is there? 100. Then 6 times 10. Then 2 times 1. So you see what's happening. It's a base 10. So each one of these numbers or these columns are base 10. This is 10 to the 0, 10 to the first, 10 to the second, 10 to the third. Anything to the 0 power is 1. That's why we multiply by 1 in this first column. 60 times 10 to the first is just 10. 10 to the second is 10 times 10, which is 100. 10 to the third is 10 times 10 times 10, which is 1000. The exponent tells us how many zeros are back there. So if I had 10 to the 6th, how many zeros do I have?
6.
It's a million. Again, it's all based. There's a reason these are called, numbers are called digits. Why are they called digits? What are these called in your hands? These are called digits. Fingers are called digits. That's the reason. So when we first counted, we counted with our fingers. So these are our number system. Again, our whole algebraic system came from the Arabic nations, built up by other countries and other people around the world after that. But this is where it all began, in Arabia, Saudi Arabia. Okay, the last one I want to talk about. Oops. The last one I want to talk about is binary. This is what computers use. We only have two numbers, binary. Since we only have two numbers, this is a base 2 system. Always start off with a 0. And you have two base 2 systems, so you have two numbers. What's after 0? 1. Remember, ours was a base what? So we start at 0, we have 10 numbers. That's 1, 2, 3, 4, 6, 7, 8, 9, 10. Anything after that goes in the next row. So what would a base 4 system look like? Yep. Those are all the numbers you can use. You cannot use anything higher. So it's whatever base number is, subtract 1, and that's the largest number you can get. So anything after that goes in the next column. We have base 10, we have 10 to the 0, 10 to the first, 10 to the second. So in a base 4 system, we have 4 to the 0, 4 to the first, 4 to the second, 4 to the third, and so on and so forth. So on base 2 system, what do we have? And so it's base 2, so we can keep on going. So if I gave you a number 1101 in binary, what does that number represent? Well, let's look at what is 2 to the power 0? Not 1. Anything to the 0 power is 1. 2 to the first power is 2. What's 2 to the second power? The exponent tells you, an exponent tells us how many times do we multiply the base to itself. So we multiply it to itself 5 times. And it's not 2 times 5, it's 2 times 2 times 2 times 2 times 2. So 2 to the 5th, 2, 4, 8, 16, 32 is 32. That's where it came from. So here, so 2 to the second would be 4. What's 2 to the third? 8. So this is our base 10 numbers, and here's our binary number. How do we convert them? It's like on and off switch. We have one of these, so that's a 1. There's none of these. I have one of these, so that's a 4. And I have one of these, that's an 8. I add up all these together, I get 13. So 1101 is equal to the number 13. To separate this, we write this. So 1101 base 2 is equal to 13 base 10. Convert that number. This is base 2. Give me a base 10 number. Also, let me show you an easier way, because we started with 1. To go from this column to the next column, we just multiply by 2. 1 times 2 is 2. 2 times 2 is 4. 4 times 2 is 8. So the next one would be 16. So 2 to the 4th would be 16. What's next after that? 2 to the 5, that's 32. 16 times 2 is 32. So when you create your columns for these, so when you get the answer, spit it out. So this first column is what? 2 to the 0, which is 1s. The next one is 2 to the 1st, which is 2. Next one is 2 to the 3rd, which is 4. Next one is 2 to the 4th, which is 8. 2 to the 5th. No, 0, 1. Oh, I forgot 2. 2 to the 2nd is 4. 2 to the 3rd is 8. 2 to the 4th is 16. 2 to the 5th is 32. Everybody okay with the columns? All I do is, since that one's on, I take that number, I add it to the next one, which is 4. And I go to the last one. I just, whatever has a 1, I add that number. The reason I get binary, light switches are binary. It's either on or off, open or closed. So it's either I count the number or I don't count it. 16 times 0 is 0. 8 times 0 is 0. 4 times 1 is 4. 2 times 0 is 0. 1 times 1 is 1. So that, this number is 32 plus 4 is 36. 37. Everybody okay with that? Are you gonna do another one, or are you okay with it? Okay, let's do another one. Yeah. This is how computers talk to each other with binary. It's either an impulse goes or it doesn't go. So each of the columns have their own numbers. So I multiply 16 times 1 gives me 16. 8 times 1 gives me 8. 4 times 0 gives me 0. 2 times 1 gives me 2. 1 times 1 gives me 1. Now I add these together. 10 plus 16 is 26, plus 1 is 27. So this number is 27 base 10. The same logic. How would I write 15 into binary? The way you convert from base 10 to binary you keep on going until the number in the column is bigger than the number you have here. Does 16 go into 15? Backwards. 15 goes to 16. So this number is too big. I don't need that column. So 8 fits in 15, right? So I subtract it. I can use this. So I subtract 8 from there, leaving me with what? 7. Does 4 fit into 7? Yeah. So I subtract it. Does 2 go into 3? Yeah. So I subtract 2. And 1 goes into 1. So 15 is 1111 in binary. So you just pretty much make your columns, and if it fits, put a 1. If it doesn't fit, don't put a 1. Okay, we know that this number here is 37. Let's work backwards. So it's 100101. So if we start off with the number 37, I want a base 2 number. Do I need the next one? The number's 37. Do I need 64? Does 64 fit inside there? No. So as soon as the number here becomes bigger than that, you don't need it. So let's begin. Can we subtract 32 from 37? Yes. So subtract 32 gives us 5. Does 16 fit in 5? No. Does 8 fit in 5? No. Does 4 fit in 5? Yes. So I subtract 4. Does 2 go into 1? No. Does 1 go into 1? Yes. So our number is 100101. Which is, well, here's an interesting thing. We saw how the Egyptians, the Babylonians, how the Mayans, what system they used. And today, our supercomputers use this, zeros and ones, the easiest way you can make it. There's no ifs, ands, or buts. It just, but we have to define the different columns of numbers. Because in our system, this is the tens, or this is the ones, the tens, the hundreds, the thousands, the 10,000s, 100,000s, and so on and so forth. So you have to have columns represented. All right, so that's it for today. We did the numeric systems. So that means we're pretty close to finishing up this chapter.